All right. Well, hello, chemists. Okay, so let me get my screen share going here. Give me a second right here to get my screen share going. And all right, let's pop over to our good friends at BitPaper. Well, hello, chemists. Right. So anyway, hello. We see Alif is with us. Well, Alif, hello. Welcome to the class. Yeah, this is the master chemistry class I run on a Sunday. All right, so here we are with this one. So we're picking up where we left off last week. So where we left off last week, chemists, was that we were looking at redox reactions. Okay, and so we looked at the definition of a redox reaction as in reduction, oxidation, loss, gain of electrons, loss, gain of oxygen. We looked at how to balance redox reactions in neutral, acidic, and alkaline media. We looked at how to deconstruct a reaction, but they give you a redox reaction into two half reactions, balance those in acidic media, and then recombine them. All right, and also put them into alkaline media. So all of that is up on the YouTube channel. All right, if you want to go back and look at this one. And so this one then, by popular request, chemists, this is student driven. All right. They did say, well, do I mind if I go over some past paper questions? And the answer is, well, of course not. Of course I don't mind. All right, so on this one, we'll wrap on this. If I can get my screen to move over there slightly, we'll wrap on this one, chemist, this module. I'll put it up onto YouTube and also on the website. If you want to take a look, you can. And so what I thought we would do then is quite simply, we would have a look at some past paper questions. So I went into my archives here, all right, and here we are with some past paper questions. And so I picked the ones that I think would be typical that you would see, all right, and so got multiple screens going here. Okay, hold on, chemistry, here we are. And so on this one then, in Air Force Blue, all right, let's try to minimize this picture, get as much real estate as possible. All right, and so here we are in Air Force Blue. Let's get going on these. And I think that I have just one more. Yep, one more to go. All right, one more question. All right, so today, a lot of past paper questions, chemists. And so if you need to, all right, by all means, I've got multiple screens going here as best as I possibly can. All right, if you have a question, let me know. Put it into the chat stream here. Okay, and any ideas of what we want to do next week, let me know. I got a few requests for, can we do acid and bases from year 13? And I said, yes, okay, we can do this one. All right, then, so here we are then. In Air Force Blue, our most excellent friends at BitPaper. I love BitPaper, really do really good products. Okay, so it says, write a half equation for the oxidation of chloride ions, okay? And so, all right, so chemists, hold on, gotta get this just right. Turn on pen like this. All right, chloride ions. Now, you think in oxidation, it means that they're going to lose an electron. Yes. And so you're thinking, now we talked about this one last time, right? We said oxidation states is what you learned in GCSE as being charge. And so the most common oxidation state, the most common charge, if you would be the chlorine -1. And we said it's tied into the number, it's tied into the valence electron. So obviously chlorine is in group 7, it's got 7 valence electrons. You could gain 1 and be Cl-, which is what we're probably thinking that it is, Cl-. However, we know that it could also go all the way up to +7. It could lose those 7 valence electrons, okay? Because we said that non-metals and transition metals, they do have what's known as a variable oxidation state. All right, so this one here then for a point, so Cl minus goes to, and obviously if it's being oxidized, all right, it's going to be Cl2 like this. Now, chemists, this is what I teach. You got to start thinking like a teacher, right? You're thinking, why are they asking you about chloride? Because they're asking you about chloride because do you know that chlorine gas is a diatomic molecule? It's trying to catch you out there. I was saying, yeah, I do. CO2 is a diatomic molecule, 1 to 7. So therefore, we did this last time. All right. Chlorine is obviously Cl minus. The oxidation state here is -1. That was easy. And then on this one, any element in its natural state is going to be 0. Oxidation state. So we've got this. Oxidation states written down. Yes. Balance for atoms changing oxidation states. Right. I needed 2 in front of this one. And then I'm thinking, all right, let's see. I got 2 negatives. So I've got -2 on this side, right? 2 times -1, -2. This is 0. And so I need to add 2 electrons onto this side. Okay. Now, chemists, again, I do realize that so some mock schemes, some exam boards do the -2 electrons on the left. No, just stick with the +2 electrons on the right if it's an oxidation, because it shows it's losing electrons rather than get into the -2 and +2 electrons. That's just way too confusing, okay? So this one right here, oxidation of chloride has got this. All right, now, it said sodium chlorate 1. All right, so chemists, this is our sodium chlorate 1 here, right? Now, again, look, there are a few polyatomics you just need to know. All right, and so ClO minus is going to be my chlorate 1. So when you're in this module, all right, what I recommend you do is I'll write these down on a piece of paper, either on Quizlet, either on Flashcard Hero, or, on a piece of paper back at the book, little index, and got right, these are polyatomics you need to know. So this is my chlorate 1 right here. So hold on. So you've got Cl minus here. So you've got ClO, hold on. ClO minus here for the reduction, which means it's going to be gaining electrons, right? To chlorine in acidic solutions. And so on this one, then I've got my Cl2 like this. All right, so here we are then. Cl2, so obviously it's going to be a molecule, any element or molecule in its natural state is going to be 0 oxidation state, right? So for example, sodium metal, magnesium metal, 0 oxidation state, oxygen gas, chlorine gas like this. And so on this one, then let's see now on this one. So let's scratch over here. Look, ClO minus. Let's work out the oxidation state here. All right. Oxygen we know is -2. Why? Because it's not a peroxide. A peroxide is something like, H2O2. All right. This is an example of a peroxide. All right. Or something weird like Li2O2. These are examples of peroxides. This is not a peroxide. This is an oxide. So oxidation state of oxygen is going to be -2. All right. And so I've got chlorine, whatever it is. All right. -2 has to equal -1, right? So I've got my value for chlorine right here, -2, which is my oxidation state of oxygen, has to equal the total charge, which is -1 on the ion. And so therefore chlorine would be +1. All right. So Sunday afternoon here at Chemist, I've got to keep the mental math going. All right. Chlorine here has to be +1. All right. So you think, got it like this. Right. Now then, 1 + 1. Written down oxidation states like we did last week. Yes, +1, 0, absolutely. Got to put the 2 in right there. All right, so here's my two chlorines, like this. Let's see, I've got to put in the electrons. Well, two is two positives, right? So two, this is positive, two on the left, goes down to 0 on the right, which means it must add 2 electrons on the left-hand side. All right. There's my change in oxidation state. It went from 2 positives down to 0, balanced, adding 2 electrons. Let's say I gotta do something with the oxygen, right? So let's say add a water, all right, to the right-hand side, and let's say I've got 2 oxygens there, so I'm going to add 2 waters like this. All right, we did this last week. 2 times 2, I've got 4 hydrogens on this side, which means I need to add 4 hydrogens on this side. Okay, so did I get that correct? I did. Good. All right then. Last bit then. Write an overall equation for the redox reaction of chloride 1 ions with hydrochloric acid. All right, so what we've got to do then here at Chemist is this bit, is we need to combine them both together. So hold on. If I change pen color from royal blue, all right. Somebody told me this is actually Syracuse orange that I'm using now. So if you follow American football, it probably seems like, Syracuse orange. Look, part A, the electrons on the right-hand side. So this is my oxidation reaction. And you're thinking, redox means there's a reduction and an oxidation taking place. And this is how I explain it. Well, if you've got an oxidation on the right-hand side, as I'm losing electrons on the right, well, something has to be reduced to gain electrons on the left. Now, all right, so this is my reduction reaction on the left-hand side. The term redox means reduction, accepting electrons, and oxidation, gaining electrons. I have 2 electrons on the right, 2 electrons on the left. Okay, don't need to worry about that. Got to make sure that the electrons balance out, chemists. And so you're thinking, if it wasn't the same number of electrons, I would multiply through by some factor so that the number of electrons on the right of the arrow would equal the number of electrons on the left. But on this one is straightforward. You just got to add them together. Okay. Let's see. And so if I do that, let's see, I got 2Cl minus. Can I scoot this up? Oh, the ink is sticking. I love bit paper. Bit paper is a very nice product to use. All right, so 2Cl minus here. I'm just adding them together, right? So I've got 2Cl minus like this, and 4H plus like this. 2Cl minus, 4H plus. The electrons cancel out on the right and left. Not worried about this. And I've got 2ClO minus like this. And so all I've done, right, 2Cl, 4H plus, 2ClO minus, done that, arrow, Cl2, all right. And let's see, now I've got Cl2 up the top, and I've got 2Cl on the bottom. Hold on, did I do something? No, hold on, that is indeed correct. I'm just checking. Hold on a minute, chemist. That's right. Yeah, 2ClO minus, 2Cl. Got it. All right, so I've got Cl2 here, and I've got Cl2 up here. I can add these two together. This would be 2Cl2. All right, and 2H2O. All right, so the 2Cl2 is like this, and the right, add together the 2H2O. And so this would be correct, but can I simplify down? This is what I was checking to make sure. who's doing this right, simplify down, meaning I can divide through by 2. And so I'm going to have what, Cl minus and 2H plus and ClO minus arrow, right, Cl2 and H2O. And that should be indeed correct. Right, it is. Good. All right, then. So here we are, 3 for 3. Now, let's see, on this one, all right, I added this in because now this is one of these, well, I wouldn't really call it like an essay question, more like, you know, just well, one of these wordy questions you just got to answer, right? So it says a solution of sodium chlorate 1 was added to a color solution of potassium iodide. All right, then, so let's see. Ding, ding, ding. So it's my sodium chloride 1. So here is my, whoops, hold on, put that there. I think I hit the wrong button there, chemist, hold on. I do these live, and so, you know, you got to bear with. All right, ClO minus like this was added to a color solution of potassium iodide. All right, and they wanted to know what's going to happen. Well, if I come up to here, you see this equation up here. All right, so this equation here, what I'm going to say is that the ClO minus is this equation up here. So I'm just going to borrow this equation, bring it all the way down here to explain this. So this explains this bit right here. And so I'm just going to say, right, the 4H plus and the 2 electrons and the 2C, hold on, that's a 2, hold on. And the 2 ClO minus goes to, let's see, Cl2 and 2H2O. Now, I'll explain my thinking in a minute, chemists. I've also got I minus like this, and I'm thinking, if this has been reduced, because the electrons are on the left-hand side of the arrow, I'm thinking, could the I minus be acting in the same way as, hold on, got a question. Hold on, ding, 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 ding. Oh, hold on, thank you, Alifa. Why wouldn't you cancel out the CO2 as it's on both sides? Okay, hold on, Alifa, right, you got to bear with, the chat stream just updated. Hold on, ding, 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 Alifa says CO2. Okay, hold on. We're going for part B. Let's see. Ding, ding, ding. Hold on. Aha. Hold on, Alifa. Is it Cl minus on the left-hand side? And is it Cl2 on the right? Are you looking at part C? Yeah. So, I know it's a bit daunting. Like, oh, I can't unmic because you know what? The entire internet is listening in for both half equations. Right, it's Cl minus on the left and Cl2 on the right. So they're not the same thing. So no, you couldn't cancel them out. All right. Because Cl minus is an ion and Cl2 is a molecule. And so they're not going to cancel out. Does that make sense? Yeah, questions are good, chemists, all right? Questions are good, all right? So please keep in the chat stream. You know, I've got loads of windows open, trying to keep up with you chemists, all right? Hopefully this is useful for you. All right, so anyway, Alifa, thank you for that. Good question. All right, then. Now, I'm thinking then that could it possibly be, well, could it possibly be that I minus All right. Is oxidized down to up to I2. You know, like Cl minus was oxidized up to Cl2. Well, could I minus be oxidized up to I2? And so this is what I think that they're getting at here, okay? So, hold on. Whoops. Oh, I hit the wrong pen. Hold on. Oh, they are right. Yeah, I was trying to draw a line. All right. So, yeah, what I'm saying is that really quick, right? Things like this. All right. 4H plus and 2ClO minus and 2Y minus goes to Cl2 and I2 and 2H2O. All right. So the reason why chemists, right, this is the logic for answering this question, all right? And look, from a teacher point of view, you're thinking, why are they all of a sudden talking about I minus? Because they're seeing, can you think of, oh, I minus is analogous, going to do the same thing as Cl minus. Therefore, I'm going to put I minus in place of the Cl minus in this half equation and add them together. All right. So this is a bit like thinking like a teacher, right? Oh, let's see. So what's going to happen? Well, iodine, all right, in solution. Yeah, that's going to go brown. All right, a brown color. Okay. And so it's going to be a brown color like this. Now it's 3 marks. Okay, so I'll look at the mark scheme real quick. 3 marks, and so you've got to build it up. And so this is what I'm saying, chemists, is number 1 then is it is a brown color for 1 mark. Now the next question is, you got to think, I wonder how I can get the other 2 marks. Well, the next question, next bit is, why is it a brown color? Because, all right, you form I2. All right, so I2 in solution, in aqueous solution, is brown. Right. And so now you're thinking for the 3rd mark, right, chemists, this is like stacking points now, right? The 3rd mark. Why is it going to form I2? It's going to form I2 because it's oxidized. Okay. And so when I do past paper questions, what I like to do is look at the point value. Very first thing I'm doing, look at the point value and thinking, right, I need 3 distinct points. Brown color, forms I2, is oxidized, right? So this was question 1. All right. So if you have any questions, let me know, chemists. If not, I will move on. So yeah, the first one then, oh, by the way, I wanted to point out, let me get back up to here. All right, the reason why I picked this one from the archives, chemist, is because a disproportionation is a fancy way of saying, right, that chlorine, all right, you ever see the word disproportionation? So in your notes, you're thinking, I wonder what he's going on about chlorine and disproportionation, because they always ask you about chlorine. Chlorine, all right, can have, oh, that's supposed to be have, either a -1 or a +1 oxidation state in a reaction at the same time. And so, hint, just start doing loads of questions about disproportionation. It's on the exam every year, right? So yes, you think, because look, over here, let's see, where's my overall equation? Right here, down here, this one here, right? So look, chlorine right here, this chlorine right here is -1, right there. And up here, see the chlorine in the chloride ClO minus, this is +1. And this is obviously going to be 0 oxidation state. And so this is the reason why they like doing chlorine as an example, because it's one of those halogens that will actually +1, 0, -1. It's an exam board favorite, okay? All right then, so hold on, I've opened up into the screen here on my trusty iPad. Okay, let's move on to question 2. All right, so this one, let's see, deducing half equations and definition of terms. All right, so we did this, we did half equations, was that glass lesson, I think it was? All right, deduce half equation for the oxidation of chloride ions to chlorine. Oh, well, that's easy, right? Because we just did that one. And so it's like, yeah, Cl minus, right? Cl minus arrow. Oxidized means it's going to lose an electron. So Cl2. So I need 2 chlorines, you know. It's obviously 0 oxidation state. This is -1. All right, so we've got 2 chlorines. I need to add in 2 electrons because 2 negatives, 2 times -1, 2 negatives. 2 electrons like this. This one done? Yes, right. And give the oxidation state of manganese in MnO4 minus. All right, so here we are then, chemists. The leading us down a path. MnO4 minus. All right, we looked at variable oxidation states. I think it was 2 lessons ago. So have a look on the YouTube for that one. All right. So MnO4 minus, and so oxygen again is going to be -2. And so you're thinking manganese, whatever it is. Now, do you notice how the variable oxidation state is always a transition metal or a non-metal? Yeah, okay. So manganese plus 4 oxygens, 4 times -2. Has to equal the charge on the ion, which is -1. And so what manganese -8 is -1. And so I got manganese being +7. Yeah. All right, then. So I got manganese then as being +7. Okay. Yeah, if you look at, I think we talked about this one in a previous lesson, right? If you look at the oxidation states of manganese, it's a D block element. And so you get into full and half full D subshells, which give you a bit of stability. All right. Now, on this one, chemist, I always talk about tripwires. Yeah, I know. Tripwire. What it means is they put something in there to go trip you up. So tripwire is this. You need to include the positive sign. That is supposed to say include. Hold on a minute. Even I can't read that. Hold on. And I wrote it. All right. Include the positive sign. You just don't put down 7. Right? They don't like that. You've got to include the positive sign. Yes, I know it's a bit redundant, but hey, it's the exam board. You know, it's up to them. All right, let's see. This one, deduce half equation for the reduction of, let's see, MnO4 minus my permanganate ion in acidified solution. All right, 2 manganese, 2 ions, and water. All right, so hold on, scroll this up a little bit here. Okay, so hold on. MnO4 minus. Now, chemists, there's a few you just got to know how to do. And in year 13, you do titrations, you do redox titrations as well. And the manganate 7 ion is the one that you'll use. And so you'll see this half equation like all the time. Okay, so MnO4 minus like this goes down to Mn2 plus, like so. Let's see. So this is +7. Just to keep track. So oxidation states written in +7 +2. Yes. Let's see. I need to add in 5 electrons on this side just to make the change in oxidation state work out. All right. That's done. Atoms are balanced at changed oxidation states. Yes. I need to add 4 waters on this side. Absolutely. All right, and I need to add 8 hydrogens on this side because I've got 4 times 2 is 8 hydrogens on this side. So really quick checking that. Yes, we got this correct. Good. Yes, yes, yes. All right. Now, somebody last week asked me about equation of state. My answer is I talk about bandwidth, meaning, you know what, just write, when you're done with the balanced half equation, just write it in. Okay, why? Because if the exam board wants it, they don't want it, you've written it, and therefore you don't have to think about it. You go, hydrogen ion to aqueous. This is obviously aqueous, aqueous, and water is a liquid, done. All right, then. Now, this one, let's see, let's scroll down a little bit. All right, no more come in the chat, that's okay. All right, so let's see, chlorine behaves as an oxidizing agent. All right, the extraction of bromine from water. All right, chlorine gas is bubbled through a solution containing bromide ions. All right, so we are then. So chlorine gas, I said CO2 gas, yes. And it's got to be a solution of bromide ions. All right, yeah. So I'm thinking, well, this has to become this. You know, because chemist, you're thinking, right, now again, look, if this is a zero oxidation state because it's chlorine gas, well, what else can I do with it? CO2, you're thinking, I guess I could break it apart into Cl minus, which would be -1. Here's one half equation, right? And then Br minus, let's say the extraction of bromine. Well, I'm thinking, yeah, you would probably want bromine to become Br2. And so this is going to be zero oxidation state. So something like this. Right. Good. Yes, that was easy. All right. One observation that I would make during this reaction. Bromine water. Okay. Now, chemists, did you notice in the previous question, it was in aqueous solution, iodine is brown. All right. So iodine is brown in aqueous solution. So again, you've probably done this practical. Okay, hold on. Question coming from chat. Is it always aqueous? Said Alifa. Yes, it's always going to be aqueous. All right. And so, yeah, you can with complete confidence just write aqueous going from left to right, except for water, which is a liquid. All right. So there's that one for you. All right. Good, good, good. All right. Loving these questions. Brilliant. So iodine is brown. Bromine. Have you done the bromine water test? You know, for alkenes, it decolorized bromine water. So bromine water is going to be orange. All right. And so let's see. I would say that it would turn orange. Okay. All right. So I would say that the solution, all right, turns an orange color. Okay. Okay. Like so. Right. So here's my little cheat sheets again. These are like, you know, the halogens in water. Like so. All right. In terms of electrons, state the meaning of oxidizing agent. Okay. So, all right. Now this is what they're going to ask you, chemists, is this. They're not going to say what's the definition of oxidation or reduction, because that's easy, right? Oh yeah, oxidation is when you lose electrons, reduction is when you gain electrons. They're going to try to trick you. So we put down tripwire. Okay, they're going to try to trick you by talking about oxidizing agent or reducing agent. And so an oxidizing agent is something which is a species which causes, here's some notes, which causes another species to be oxidized. Another species to be oxidized. It's an oxidizing agent. It causes another species to be oxidized, which means that if its oxidation means that species has lost electrons, well, then this means that it must gain electrons. Because those electrons the other species has lost, because it's being oxidized, they have to go somewhere. So it's got to go to the oxidizing agent, right? So it must be reduced and gain electrons. All right, so we've seen that, chemists. Look, this is what I mean by tripwire, right? They're not going to take an easy definition. They're going to take one that's a bit tricky and just see if you know what to do with it, right? So oxidizing agent means it's accepted the electrons from something else, and so therefore it itself has been reduced. Okay, so there was this bit right there. No more on this. Okay, let's see. Okay, and I think this one is going to wrap up the bit on chlorine for us. I was picking these questions. I thought they'd be useful. All right, so hold on, let me scroll this a little bit, give some real estate here. All right, let's see. Chlorine, again, look, chlorine and water. All right, let's see, give me the equation of this reaction. Okay, and so on this one then, chemists, what I've got is I've got chlorine gas, and so you're thinking like swimming pools, right? So like, you know, oops, hold on, wrong button. All right, gotta do it live, chemists. All right, so look, chlorine, Cl2 like this, and it's going to be, it's in water, it's been bubbled through water. All right, now this one, chemists, well, not too much going on. You're thinking, right, you see the Cl2 here. The Cl2, well, the only thing it could possibly do is become Cl minus, right? But you've got water, which is obviously this. And so I'm thinking, well, could I pull a proton off of water? This Cl minus does not want to be Cl minus, okay? You're thinking, no. So therefore, it's going to pick off a proton, and so this become HCl, all right? Like so, positive one charge on the hydrogen there. And let's see. Hold on, got it right there. Let's see. And then, hold on, ding, 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 ding. Right, hold on, form. Doc says, what to slowly form oxygen? Oh, and so it can form oxygen. Also, be left is O2. All right, so this is what I'm thinking then, yeah. So the chlorine went from oxidation state of 0 and it went down to -1, right? It picked off a proton because Cl minus is not going to be happy on its own. It's going to pick off a proton and give you HCl like this, and you're left with O2. And so not going to balance it because otherwise it's just going to be weird. All right, so let's see. I've got 2 chlorines in here, Cl2 here. I need 2 chlorines over there. All right, so my 2 chlorines done, but check mark over the chlorines. We've done that bit. Let's see. Oh, I've got 2 oxygens on this side and I've got 1 oxygen on this side. And so I'm going to put a 2 in front of here. So 2 oxygens. Yeah, 2 oxygens like this. And let's see. Therefore, I'm going to have to update my HCl here, right? Because I'm going to change this from being a 2 to being a 4. All right, to make sure this balances out, there's now a 4. And so there's a 2. All right, so started off, just balanced the chlorines, then I looked at the oxygens, and I went back and forth until I got this. And did I get that right? Oh, I did. Good. All right. Now it says the oxidation state of chlorine in the species formed. That would be -1. All right. It's an easy point there. Okay. And then look, this is a tie-in, if you would, chemists. All right. You know, one of these synoptic links, they're now going to add in something else. You think, well, hold on, what on earth does the boiling point of chlorine have to do with bromine and what we're talking about, redox reactions? Yeah, this is like one of these compound questions. They like shove all the concepts in. See, chlorine is a lower boiling point than bromine. All right, so for 2 marks, then don't you take a look, right? 2 marks. Could it be? Could it be? Hold on. CO2 versus bromine. Okay, and they're talking about boiling point, right? So I'm thinking then is this, chemists? Boiling point has to do with intermolecular forces. So straight off the bat, I'm going to write down the intermolecular force. Chlorine versus bromine. Let's take a look. Could it be, well, if you go down the list, it couldn't be hydrogen bonding. No. Couldn't be dipole-dipole. No. It's got to be van der Waals forces, all right? So the only IMF present is van der Waals forces. Because if you look and say like a chlorine to a chlorine, right? Yeah, there isn't any dipole there. And of course, there's no hydrogen involved. It's got to be van der Waals forces. So, could it have to do, van der Waals forces, could have to do with the size of the atom? You know, I'm thinking, you know, chlorine, bromine on the periodic table. Yeah, going down, wouldn't the atomic radius just increase? And so therefore size of the atom. So I would say that chlorine has a smaller atomic radius. True. So less van der Waals forces between the molecules. So the boiling point is less. Yeah. So do you see, chemists, right? 2 marks. Think of it like vertical stacking, you know. You got to put down the fact, then you got to explain why. So boiling point is less because less energy is needed. To break the IMFs, all right? So you kind of went on a deep dive on that one, but there you are. All right then, so hold on, move video link. Okay, so, oh yeah, the extraction. And so look, what we've done is we've done just like the writing of half equations, yes. We did the one which was the disproportionation of chlorine, which is an exam board favorite. And the other one is metals. All right, so looking at metals then, right? Let's see, titanium cannot be extracted directly from titanium 4 oxide. And so I've got what, titanium. Now, titanium 4 means that titanium is obviously in the +4 state. Oxide, well, oxygen, you know, is -2. And so I need 2 oxides, 2 oxygens to balance out the titanium here, the charge in the titanium. Right. And if I add that to carbon, is what they're saying. All right. Question is, would I get pure titanium? No, I wouldn't, because the carbon, you know, I mean, it's got the titanium is going to be reduced, has to be reduced down to titanium metal. What's the oxygen going to do? What's the carbon going to do? So I'm going to say you're not getting pure titanium metal. Why? Because, well, the carbon and the oxygen are going to replace each other. So you're probably going to get something like titanium carbide or something. Okay, right. Why? Well, because one of the oxidation states on, carbon is -4, isn't it? So you're thinking titanium carbide? Yeah. Now, for a mark, this was it, right? Hold on, question going in. Oh, I love the questions. Why can't you get titanium and carbon dioxide? Hold on, Letha. Why can't you get titanium and carbon dioxide? Because, got it. Right. The carbon, right? You see the carbon. Carbon is in the neutral. It'll go to something else, and so carbon's going to have a half reaction, right? Meaning the carbon which is in the neutral state 0 has to go to something. The oxygen, which is in -2, which is in -2 over here. Actually, this is going to be right here. Hold on. This is going to be -2. Is going to go down to 0. Okay. O2 like this. And so you're thinking, right, look, 2 oxygens like this goes down to this and 2 electrons. And so the oxygen is going to be oxidized. And then you've got the carbon doing something, don't know what it's going to do. And then we're saying that the titanium right here in the +4 state we're hoping to go down to titanium metal and 4 electrons. But the problem is that you've got 3 things present. You've got the oxygen half reaction, you've got the titanium half reaction, and you got the carbon half reaction. And so it's kind of like, well, there's too many half reactions. The bottom line is there's too many half reactions, number one. I would need a 4th one to make everything balance out, wouldn't I, number one? And then number 2 is you're thinking, right, the titanium and the carbon, they would just combine to give you titanium carbide, because titanium carbide is going to be energetically, you don't spell energetically like that, favorable. Energetically favorable. So don't know, have you done Hess's law diagrams yet? I don't know if you have. We'll have to do Hess's law diagrams, but bottom line is that energetically, titanium and carbon, they're going to combine to give you titanium carbide. Okay, so this is the reason why straight off the bat you can't have titanium being there's 4 electrons to the side, isn't it? Hold on. Titanium being reduced down to titanium metal. Okay, so there's that reason, and the last reason is in electrochemistry you do the reactivity metals. Okay, that's the other one, the other reason. Yeah, so I know there was a lot of hand waving on that one, but that's just the reason why. And then in year 13 we can pick this up as well. Okay, so here we are then. Titanium steel is an alloy of titanium and iron. Ilmenite, FiTO3 in a 2-stage process. All right, so a lot of stuff here that you don't really need. Come down to the question here. Whoops. So hopefully, Alifa, did I give you at least some kind of an answer? All right. I'll put a post-it note in that, and then when we do Hess's law, we can always come back and take a look at this one again, right? So here we are on this one. Let's see, write an equation for the reaction of Fi. Oh, okay. FiTiO3. All right, this is ilmenite. Okay, never heard this one before. It says with chlorine. All right, so hold on. Dang. With chlorine and carbon okay, to produce iron 3 chloride. Oh, very nice. Look, it actually gave us everything. Iron 3 chloride and titanium 4 chloride. Oh, this is an easy point. All right, and carbon monoxide. All right, and so here we are then. What they want to know is on this one. Okay. Right, got to balance this one, chemist. And so I'm thinking one iron, right? One iron right there. Now, let's see, titanium. All right. Let's see. Oh, I've got 3 oxygens here, right? See these 3 oxygens here. I'm going to put a 3 in there. So at least my ions are balanced. My oxygens are balanced like this. Okay, my titanium looks like it's balanced already, like this. That is good. Right, now I've got 4 chlorine. Oh, I've got 4, 5, 6, 7 chlorines on this side. So I need 7 chlorines on this side. So what, 7 over 2? All right, now you can leave it in fractional state. You can multiply through by 2 at the end, but 7 over 2 times 2 is 7. So my chlorines are balanced, and it looks like I need a 3 in front of this one. All right, so they're asking, well, why is it that they did this question? Well, simple, chemists, I just wanted to see if you can deal with fractional coefficients, okay? And the fact that chlorine is in 2 compounds on the right. Okay, trying to catch you out there. All right, so there's this one. Let's see. It says write an equation with a simultaneous reduction of the mixture of iron 3 chloride and titanium 4 chloride. So hold on, iron 3 chloride, FeCl3, and titanium 4 chloride, or TiCl4. All right, to iron, Fe, and titanium, Ti. And it says using sodium. And so using sodium, all right, how I'm reading it is for using sodium. This must be a reactant. It's got to be on the left-hand side, right? Now, chemists, what they're doing is that they're doing one that you've never seen before. And this is normal for the exam board. All right, it's always like throw you one and go, I've never seen it before. Okay, so iron, titanium, 4 chlorines on this side. Okay. And I got sodium on this side. All right, so what I'm thinking then, chemist, says straight off the bat, then I'm thinking, hold on a minute. I don't have a product on this side that contains chlorine, but I've got chlorine coming in. This is going to be Cl minus. Could it possibly be reacting with the sodium to give you sodium chloride? Yes, it's going to be like positive. It's going to be -1. All right. This is my first thing I put down. All right, number 1. And then let's see. Then after that, what I got to do is we just got to balance it. So let's see. 1 iron, titanium. So chemists, all they're doing on this, look, they're just giving you, a situation you've never seen before, and just seeing what if you can apply your chemistry knowledge. Okay, so hold on, am I on the right one here, chemist? Hold on, ding. Yes, I am. Right, so let's see, iron, titanium. On this side, I got 4, 5, 6, 7 chlorines. So I need to put a 7 in front of this one. 7 sodiums. Let me check. Did we get this balanced? Yes, we did. Good. All right. Now, so far, right? So good so far, right? Yeah, coming in. All right. So it says scrap iron is used to extract copper from aqueous solution containing copper 2 ions. All right, what happens to copper 2 ions in this that should say extraction. All right, put the N back in, don't know where that went. All right, so I'm thinking, right, again, look, copper 2 ions, right? This is how I'm thinking, chemists like this, thinking if they want to extract it, that means that they want it, you know, as a solid, they can get rid of it, you know, out of the solution. So copper like this. And so I'm going to have to add right there. Let's see. Copper 2 with 2 electrons like this. And so, yeah, this is going to be a solid, right? Like this. And then you got the iron, scrap iron. So they're putting the iron in. Well, I'm just going to take a guess that iron is going to be going down to Fe2 plus and 2 electrons, right? Now, chemists, on this one, you're thinking, right, iron has a +2 or a +3 oxidation state, right? It could be Fe +2, could be Fe +3. Which one is it most likely to be? Answer Fe2 plus. Why? Well, simple. Energetically favorable, because every time you remove a valence electron, it takes more energy to do so. So therefore, the lower oxidation state is more likely. Okay, and so let's say the copper ions, then they have been reduced, haven't they? So copper ions have been reduced. Okay, that's what I said. Copper ions have been reduced. Let's see. Just checking mark scheme right here. That's exactly what they said. All right. So yeah, 2 marks. They've just been reduced. They've gained 2 electrons, haven't they? Because the overall expression is this. You know, copper 2 plus and Fe goes to copper solid and Fe2 plus, right? All right. So moving on. Okay, aluminum is an expensive metal because it's extracted from molten aluminum oxide using electrolysis. Half equation that occurs a positive electrode during this extraction. All right, so this one, chemist. Okay, so hold on. So, so yeah, go on. It's obviously aluminum oxide, right? Like this, yeah. So I'm thinking, right, aluminum in the 3+ state goes down to aluminum like this, and they're gonna have to add 3 electrons in. Okay, so let's say at the positive electrode, and so we haven't done electrochemistry yet, but the positive electrode is where the reduction is going to take place. All right, so let's take a look. And so this is my 1/2 equation, right? And the other one then has to be something to do with the oxygen. Well, this is obviously -2 oxidation state here. This has to go up to O2 like this. I need two oxygens to balance this out. And now this is a bit you got to think, right? You're thinking this is 0 oxidation state. So each oxygen is going to lose 2 electrons. I've got 2 oxygens, so therefore I would have to have 4 electrons, okay? And so this one is what's happening at the positive electrode here, right? Positive electrode. All right. And when we do electrochemistry, chemists, we'll talk about positive, negative electrodes and everything else. All right. There's this one. All right. Let's see. Just looking at time, chemists real quick. All right. I tell you what, let's do one more. All right. Because I think you got the idea now. All right. I do keep these to about an hour. All right. So oxidizing agent. And so oxidizing agent, then chemists, hold on, hit the wrong button. All right. Oxidizing agent is something which is reduced So it's something which gains electrons, right? Because you're thinking, yeah, oxidizing agent, it causes something else to be oxidized, therefore itself, it must be reduced, so it's got to gain the electrons. Let's see. The element X in the ionic compound MX, explain the meaning of the term oxidation state. All right, well, the oxidation state, what does this mean? Well, you know, at GCSE, you knew it's the charge on the ion. It's the charge. We just call it oxidation state at A level. Okay. All right. Let's see. Let me scroll this up a little bit so I can see it. All right. Okay. Oh, this is easy. All right. So this is just, again, chemists, do you notice that they're always going to ask you for a non-metal or a transition metal, because those are the ones that have variable oxidation states. And so carbonate, CO3, 2 minus, all right, CO3, 2 minus like this. Your oxygen has to be -2, all right, because obviously it's not peroxide. And so carbon plus 3 times -2 is -2. I'm thinking carbon's +4. Okay. Now, chemists, +4, right? Not just 4, +4. But again, stop thinking, you're thinking, carbon being +4, could it lose its 4 valence electrons? Yes. If you had to say carbon be +5 or +6, well, that's just not going to happen because you didn't the noble gas core, right? And phosphorus in PCl4 plus. So PCl4 plus like this. All right. Chlorine is going to be -1, most likely oxidation state. And so phosphorus -4 is +1. And so this is coming in as being +5, right? And again, does phosphorus have 5 valence electrons it could lose? Yes. And then the last one in magnesium nitride. Let's see. Well, magnesium is obviously going to be +2. It's a fixed oxidation state. It's in group 2. And so +2, and there's 3 of them. All right. And then you've got 2 nitrogens. Wherever that is, figure this out now, has to be 0, no charge in the compound. And so 6 plus 2 is 0. Let's see. Or 2 nitrogens, I should say, 0. So therefore, what nitrogen is -3. Yeah. Right. So there's this one. All right, we'll begin to wrap this from chemists, okay? Because time is moving on. All right. Oh, this one. Right, here we are then. Last bit. Right, nitrate, NO3 minus. Okay. Whoops, hold on. I think I jumped the gun a little bit. Oxidation state of copper. What's easier? It's a copper, yeah, solid. Arrow goes to copper 2 plus, aqueous, and 2 electrons. All right. Oxidation means that the electrons are being released from the right-hand side of the arrow. Okay. Nitrate ions, nitrogen monoxide. So what? NO3 minus 2. Nitrogen monoxide, NO, like this. All right, let's see. This is going to be, hold on, +5, right? Because 5, each one of these is -2. So 5 minus 6 is -1. And then this is going to be +2 and -2 like this. All right, then. So let's see. 5 down to 2. All right, if I got the nitrogen balance, the element to change to oxidation state, yes. 5 down to 2 means I need 3 electrons on this side. Okay. 3 oxygens on the left, 1 on the right means I need to add 2 waters in to make it balance out. Hold on, ding, 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 ding. Hold on, chemists. Ooh, hold on. I see. All right, so hold on. Just look the marks and there's an error on it. They did nitrogen dioxide, NO2. All right, so let's see. And then I got 2 times 2. I need 4 hydrogens on this side to make it balance out. There's this bit, and then overall equations when you add them together. All right, so this is what I was talking about earlier, chems. Look, I got 3 electrons on the left, 2 electrons on the right. So I've got to balance electrons multiplied top by 3 on the bottom by 2. Let's see if we can do this together right here. So 3 coppers, 3 coppers, and multiply through 2 times 4 is 8H plus, like this. And the electrons cancel out. No worry about this bit. 2 NO3s. So multiplying through them, adding together what's on the left-hand side. And then let's see, 3 copper 2 plus and 2 NO. All right. Let's see, 4 waters like so. Right. Now, can I simplify down? Like, did anything cancel out? No. And so let's say solid, but put this in aqueous. All right, hold on. Aqueous, or nitrogen monoxide is a gas, and this is a liquid, right? So there you are, chemists. Kind of a crash course in, I just picked like a few questions there that I thought you may find useful. Okay, hold on. Another question coming in. You are more than welcome, Alifa. Thank you for that. All right, thank you for that. Thank you for showing up. I do appreciate it. All right, and well, I'm here every Sunday, and so if you have a question, like anything you want me to cover next week, by all means, just put something in the chat stream. I mean, like email me or whatever. Okay, but on that note, let's call it a wrap then, chemists. Hope you found it useful. We did the extraction of the metal. We did the half reactions and everything else. And so next week, it looks like it's going to be back to year 13-1 on acid and bases. All right. So everybody have a great day. Have a great week. And I'll see you next time. All right. So take care.